Okay, so we are on Unit 7, Day 3, and this is video number 3. We're going to be looking at an example here where we have a rational function and we want to look at the behavior of the graph around the asymptotes. So we're going to look at what asymptotes there are and how to illustrate those asymptotes with proper limit notation, and then drawing a sketch of that graph. So first I'm going to look at my vertical asymptotes for my function here. I'm going to rewrite this in factored form. X minus 3, x plus 2 on the bottom there. And we can see that our vertical asymptotes are x equals 3 and x equals -2. From here, we're going to talk about the behavior around those asymptotes in terms of whether it's approaching positive or negative infinity for each of those kind of pieces. So I'm going to use a table, but you can absolutely feel free to use just test values. So you could test like 2.99, 3.01, -2.01, and -1.99, and test those in the original function. That's just kind of a lot of typing stuff into calculators. If you prefer that though, absolutely that's fine. So I have a 3x in the numerator, x minus 3, x plus 2. Again, I was not able to use calculators in university for my first and second year, so I kind of got in the habit of doing things this way. So I'll have x approaches -2 from the left, x approaches -2 from the right, x approaches 3 from the left, and x approaches 3 from the right. And then we'll just kind of analyze the signs of the function in each of those locations. So here, if x is approaching, well actually depends which way you want to look at this. This 3x, it depends on the sign of x. So this is going to be negative when x is around -2 and positive when x is around +3. X minus 3, that's going to be negative for sure. If you have any number around -2 and you subtract 3, it's going to be negative for sure. If you're around 3 from the left and you subtract 3, like a 2.99, that's going to be negative. But if you're a little bit above 3, that'll be positive. And then this one, x plus 2, if we're a little to the left of -2 and you add 2, it's still going to be negative. It'll be a tiny negative number. If you're a little to the right of that -2 and add 2, you'll get into the positives. And of course, anything around +3, if you add 2, you get a positive. Here, looking kind of overall at what's happening from my function here, we've got the 3 negatives across would give a negative here. So this is approaching negative infinity at that point, at that side of the asymptote. Here, negative, positive gives a positive, so it's approaching positive infinity around that side of the asymptote. Negative or positive is a negative, so it's approaching negative infinity. And 3 positives would give you a positive. On that side, it's approaching positive infinity. So I'm going to summarize this just with really nice, clear limit notation. And I'll try and squeeze it in here, and we'll do the horizontal asymptote on the next page. So I would say the limit as x approaches -2 from the left of my function f at x is negative infinity. So that's that first one. As x is approaching -2 from the left, we go towards negative infinity. The limit as x approaches -2 from the right of f at x, remember you need it like an operand, you need the limit of that you're taking of something, is positive infinity. Then both sides of the 3 down here, the limit as x approaches 3 from the left of f at x is going to be negative infinity, and the limit as x approaches 3 from the right of f at x will be positive infinity. So this is the summary that I need you guys to show using that good, clear limit notation for either side of any vertical asymptotes that you have. Now I do have another page there. So I'm also going to take a look at the horizontal asymptotes. So remember that the horizontal asymptotes happen as you approach infinity. So this is the limit of the function as x approaches infinity or negative infinity. Okay, so I'm going to say this is the limit as x approaches infinity of 3x over x squared minus x minus 6. So I'm going to divide out an x squared out of each term. I show that as kind of a factoring out and canceling. You could also look for this highest exponent of x, and you can write that as multiplying both the numerator and denominator by 1 over x squared. So here, if I multiply 3x by 1 over x squared, the x's will cancel. I'll get 3 over x. Multiplying x squared, I get 1. Multiplying the negative x, I get minus 1 over x, and then minus 6 over x squared. So each of these, except for this very first one, will tend towards 0 as x goes towards infinity. So I can evaluate this limit by saying 0 over 1 minus 0 minus 0, which of course equals 0. So the horizontal asymptote is y equals 0, which we would have known from the advanced functions way of just looking at what the highest degree of the numerator and denominator are, but this just kind of shows it in a more rigorous mathematical way using that limit notation. The other thing we want to do is test large values. So you could test like f at 1,000 and f at negative 1,000 and see, are those values above or below your horizontal asymptote. So I'll test the positive 1,000 and I get that this is about 0.003, and testing the negative 1,000 I get that that's about negative 0.00, about 3 again, that'll round there. So I need to do kind of a good form limits statement here, that the limit, I'm just going to put it on the bottom so I don't have to squeeze it in. So the limit as x approaches infinity of f at x is 0, because the limit is 0. That is my horizontal asymptote, but it's 0 from above. So I'll put a plus there. And then the limit as x approaches negative infinity of f at x is 0 from below, because that's a little bit below my horizontal asymptote. So I can put all of this stuff together and get a reasonably good graph of my function here. So I'm going to set up my graph. Remember that you're going to want to do your asymptotes with a dotted line. Make sure that you're putting them in there and labeling. And if it's right on one of the axes, I always just draw it like just a little bit above, just so that it's visible. or use a different color, that kind of thing. So this would be y equals 0 for my horizontal asymptote there, and the vertical asymptotes were at -2 and +3. So here we want to be able to really clearly graph this end behavior. So the first one, because I'm already got it on this page, I know that as x goes to positive infinity, it approaches 0 from above. And as x goes to negative infinity, it approaches 0 from below. So I'm going to put that on my graph, just kind of towards the end of the x's, it's going towards 0 from above. And then towards the end on the other side, it's going towards 0 from below. So those are kind of my end behaviors around my horizontal asymptotes. Looking back at the other work we did, we knew that around -2 from the left, it was going towards negative infinity, and around -2 from the right, it was going towards positive infinity. So on the left side of this, the vertical asymptote here, it's going to the negative infinity and then to positive infinity. So we're just kind of like filling in this end behavior. Now the 3 from the left side of the asymptote at 3, it was going to negative infinity, and from the right, it was going to positive infinity. So kind of like that. And once you get that, we can actually do a really pretty reasonable graph here of this function. One thing that I really want to draw your attention to, I think everybody's probably okay with this section here, and maybe I got a bad angle, but kind of that section there. This middle section, a lot of people get mixed up with not wanting to cross this horizontal asymptote, but you absolutely can cross a horizontal asymptote. It just describes where the function's going to at the ends of the function. In the middle of the function, it can do whatever it wants. It can cross it, actually even a bunch of times. So one thing that we could find from here is, like, if we just wanted to check the y-intercept, if we put in x equals 0, we're going to get a 0. So I know that that point there is my intercept. That's just kind of can give you a little bit of easy guidance in terms of how to graph this. So I'm going to bring this function down through here and go down that way. So don't get hung up on not wanting to cross. I've seen people do some really weird stuff here, knowing that it goes here and goes there and trying to avoid crossing that horizontal asymptote. I've seen people like loop it around or stop the function somewhere in the middle. It's allowed to cross a horizontal asymptote. It's different than a vertical asymptote in that way. So that is just kind of an example of how we can get some good detail on the shape of a function, and how you will be expected to show a bit more rigorous written form of the description of what's happening at your asymptotes now that you know how to use that limit notation.